Hey YouTube, welcome to the next part on differentiation. We're going to continue on from first principles. We're going to generalize the results and use those results to differentiate loads of functions. Then at the end, we're going to do a slightly more worded question. So following on from the last video using first principles, at the end, I differentiated from first principles x squared plus x cubed. And after differentiation through the cancellation of h and making h tend to 0, we got the result 2x plus 3x squared. Now you might be able to see a pattern. X squared became 2x, x cubed became 3x squared. So it looks like the power somehow ends up as the coefficient, and then the power is decreased by 1. So this is x to the power 1, yeah, before it was 2. And that's the general rule for power functions. So when you have a power function, so x is in the base, and you have a number at the top, so in the form ax to the power of n, a is just a number, n is just a number, then dy by dx equals nax to the power of n minus 1. So you can see this power of n has come to the coefficient to multiply by whatever coefficient might still be there. And then the power decreases by 1. Now you have to make sure you first bring down the power and then knock 1 off the power. And now a lot of students, they come to me and they talk about chain rule. And they say, Neil, this is called chain rule, right? Now, one thing to make clear is chain rule is a process of differentiation. Chain rule actually applies to many different functions. We use chain rule to differentiate exponentials, which we do in year 12. We use chain rule to differentiate trig functions. So chain rule is just a process of differentiation. It's specific right now to power functions where the process of chain rule brings down the power, knock 1 off the power. But I don't want you to have that misconception that chain rule is only bring down power, knock 1 off the power, because it's not. So specific to power functions, the chain rule is to bring down the power, knock 1 off the power. So let's practice that. Differentiate these functions with respect to x. So if we have x to the power of 4, we first bring down the power, so it becomes the coefficient, and then we knock 1 off the power. Part B, 4x squared. So here we have to bring down the 2 first, but because there's a 4, we do 4 times 2, 8, and then we knock 1 off the power, so just power 1. Now this one's an interesting one, 8x. Now there's different ways you can approach this one. So it's 8x to the power of 1. You bring down the 1, so 8 times 1 is just 8, and then you knock 1 off the power, power 0. But we know x to the power of 0 is just 1, so we're just left with 8. Now, what some students think is they think if you just have a number x, the x disappears. Now, it is kind of true, but there is some reasoning behind this. Remember, differentiation finds the gradient, right? So if I asked you to draw the graph of 8x, you would draw a line that looks like this. Then if I asked you what's the gradient of this function, you would say 8. It's the coefficient of x. So that's why the x disappears. It doesn't really disappear, but you're looking at the function of 8x and the gradient is the coefficient of x. Similarly, when you look at a constant, what does a constant differentiate to? Well, if I asked you guys to draw the graph y equals 2, you would say it's a flat line like this. Then if I say, okay, well, what's the gradient of a flat line? You would say 0. So you need to remember that all constants differentiate to 0, so they disappear because they all have 0 gradient. They're all flat lines. All right, so let's apply that principle. So we have 12x to the power minus 5 over 4. So the first thing we're going to do is we're going to do 12 times minus 5 over 4, x. Then you have to take away 1 from the power. I'm going to give you guys a top tip. How would you subtract 1 from a fraction? You just do the numerator, take away the denominator. So we do including the minus. So minus 5 minus the denominator of 4 is minus 9. Then you have to maintain that denominator. All right, 12 times minus 5 over 4, the 4 cancels the 12 3 times. 3 times minus 5 is minus 15. Next one, 1/6 x to the 4/3. So the 4/3 comes down. And then we do the numerator minus the denominator would just be 1/3. Here the 6, if we divide these by 2, we get 2 and 3, so we get 2/9. Remember, you could do all this in the calculator if you want. Part C, now, if you guys see multiple terms, no problem, you just differentiate term by term. Remember, in last lesson x squared and x cubed, they became 2x and 3x squared. So you just differentiate individually. Yeah, provided there's a plus or a minus in between, they are different terms. If they're two functions being multiplied together, then it's slightly different. Either you simplify, or in year 13, we do something known as the product rule. All right, so going term by term, differentiating 2, well, remember 2 is a horizontal line, so we differentiate, it just goes. We have minus 7 times minus 2, yeah, bringing down that minus 2, x, then take away 1 from the power would become minus 3. Then we have plus, then bring down the minus 3 over 2, so it's not plus anymore, it's minus 3 over 2, x, then take away 1 from the power. We do the numerator, or minus 3, subtract the denominator, would be minus 5 over 2. So when we clean this up, minus 7 times minus 2 is 14x to the minus 3, minus 3 over 2, x to the minus 5 over 2. And this is your answer. You can obviously convert back. When we solve, we don't like negative indices, so you'd write 14 over x cubed, and here you'd write 3 over 2x to the power of 5 over 2. But if it's just a standalone differentiation, you don't need to do that. All right, now we're getting to some index conversions. So cube root of x. We need to rewrite this as an explicit power function. That'll be x to the power of 1/3. Now we can differentiate, bring down the power, x, knock 1 off the power, do the numerator minus denominator. 1 minus 3 is minus 2 over 3, and that would be your solution. Hey guys, I hope you're enjoying the video. If you're new here and you want more maths content, then please consider subscribing. If you're learning something, then hit that like button and comment down below to let me know what you want to learn next. I hope you enjoy the rest of the video. Okay, next one. When we deal with fractions, again, you need to rewrite them so that they are explicit power functions. So they just need to be x to the power of something. So we need to bring this up. So it becomes x to the power of minus 2. Then root x is x to the power of a half. And now we can differentiate. So bring down the minus 2, x, take 1 away from the power would be minus 3, plus bring down the half, x. Then we do numerator minus denominator. 1 minus 2 is minus 1 over 2. And that's your solution. Okay, 1 over 4x minus 9x. This is one of the most common mistake questions where what students do is they write this as 4x to the power of minus 1. They want to bring up the x. Yeah, we know 1 over x is x to the minus 1. But the 4 does not come up with the x. Say I just covered up the x. What number is this? The number is a quarter. So when you bring the x up, the 4 doesn't come with it because the coefficient is 1/4. So it needs to stay like that. So it's 1/4. It's 1/4 x to the minus 1, then minus 9x just stays. All right, so bring down the minus 1, so we get minus 1/4 x, take 1 away, minus 2, minus 9x. Remember, that's a line with minus 9 gradients, so yes, the x disappears, but we know why now. Part C, root x. I'm going to just start doing the conversions. That's x to the power of a half times x minus 3. But now we need to expand the bracket. So this is power 1, so we need to add the powers. A half plus 1 is 3 over 2. And then x to the half times minus 3 is minus 3x to the half. Now we can differentiate. So we get 3 over 2x. 3 take away 2 is 1 over 2. Bring down the half. 3 times the half is 3 over 2. X. Then 1 take away 2 is minus 1 over 2. Finally, part D. So we have x plus 2 over cube root of x, which we can write as x to the power of a third. Now, during the last lesson when we did the limit and f of x plus h minus f of x all over h, we split the fraction because we wanted individual terms to differentiate. Same thing here. We need to split the fraction. So we're going to write it. You can do this in stages as well. You can say it's x over x to the power of a third plus 2 over x to the power of a third, and simplify. So when we divide, we take away the powers. 1 minus a third is 2/3. And then we've got 2x to the third. We bring that up. That'll be 2x to the power of minus 1/3. And now we can go ahead and differentiate. So we bring down the 2/3, x. 2 minus 3 is minus 1 over 3. 2 times minus a third is minus 2/3, x. Then minus 1 take away 3 is minus 4 over 3. And that's that. So just one last question, just to check and apply it to some actual curves. So it says a curve has this cubic equation. Find the gradient of the curve at this point. So we're not using first principles here. All we need to do is we take our curve, and whenever we see the word gradient, we always think differentiation. Yeah? We're not doing straight lines anymore. So when we see curve and gradient, we differentiate. So x cubed differentiates to 3x squared. X squared differentiates to 2x minus 4x. Remember, that's a straight line with gradient minus 4. And the 1 is a horizontal line, so that just disappears. If they want the gradient at this point P, all we need to do is substitute x is minus 1. Now the notation to say you're subbing in minus 1 is this. Yeah? All that means is you're replacing all the x values with minus 1. So replacing all the x's with minus 1, we've got 3 minus 2 minus 4. 3 minus 2, 1 minus 4 is minus 3. So there's your gradient at that curve at that given point. Part B. Given that the gradient at the point Q on the curve is the same as the gradient at P, find the coordinates of Q. Okay, so essentially what's happening here is, just for your context, say we just have this cubic. We've said at minus 1, 5, in fact, it would not be on this side, but just for this sake, we're going to say, just say you have minus 1 is over here, and you have some gradient. There's going to be another point Q that has the exact same gradient, maybe here, where the tangents have the exact same gradient. We want to work out what that is. Obviously, here in part A, the gradient was minus 3, and these are positive gradients, but it's just a quick sketch just to explain why there's another point with the same gradient. So at this point Q, it must have the same gradient, meaning dy by dx is also minus 3. Then what do we do with that? We just sub into here and solve for x. And because it's a quadratic, we should get two values, right? So we get minus 3 is 3x squared plus 2x minus 4. Add the 3 over, so we get 3x squared plus 2x minus 1. And now we just need to factorize. So we have 1, 1. We have to have 3x and x. And what's going to make a plus 2 is if we have this being plus and this being minus. So we have one solution, 1/3, and the other solution, minus 1. Now you might recognize that one of those solutions we know already. X is minus 1. We know that's the point P. That's the point P. So the point Q is 1/3, and that's the one we're interested in. So all that's left is we need to find the y value. And for that, we're going to sub that into the calculator. Easiest way for me to sub this in, I think, is to do 1/3. Let's store it as a. And then we're going to do a cubed plus a squared minus 4a plus 1 minus 5 over 27. So the coordinates of Q is 1/3 and minus 5 over 27. And that's the answer to this question. So that's it, guys. Now I've shown you how first principles now links to questions where we don't need to keep doing the proof. So we found the general rule for power functions. So stay tuned for next lesson where we're going to look at tangents and normals. So if you learned something, please hit that like button and subscribe if you want more maths content. I look forward to seeing you in my next video. Peace.